এখানে কি কোনো একটা লাইট ছিল? এই জায়গাটা একটু অন্ধকার মনে হচ্ছে।
ওইখানটা একটা লাইট আছে।
চারটি তো জ্বলে স্যার এখানে।
হ্যাঁ?
চারটি জ্বলে আছে।
ও, এইখানে লাইট নেই না, আগে এর উপরে একটা লাইট ছিল।
ওটা নিচে ছিল, নিচের ঘরগুলোতে ছিল।
I hope the board is visible for all of you. Please try this problem. We have already solved similar ones. This example is certain is there in slotting book. I am quoting it because you can easily then relate it with system description that I wrote at the beginning. Michi, have you studied Lascelles?
Yeah.
especially the first one. See, the second one we already solved, right? Nonlinear spring mass damper system. For that too, when we started with the Lyapunov function, of which consists of potential energy plus kinetic energy, then we found ultimately we couldn't establish negative indefiniteness, right? We couldn't establish asymptotic stability because it depended only on x dot probably, x which is x nothing but x2. So then we had to apply the Lassalle's inference principle probably 2 days back, right? This is Friday, maybe last Friday we took this example. Please check your note, you can easily find it. Now that is first you try to match its structure with this. That is, if I represent this one as x dot equals to x2 and x2 dot equals to some function of x1 and some function of x2 which has this property. Now see, directly it was written, that is x dot into b of x dot always positive and x into c of x is always positive. So here this bx dot, that is nothing but h2 of x2 and this cx, this is nothing but h1 of x2. Now I hope you can relate, right? So if this is the situation, then you try to analyze the stability. Of course here you were going to achieve only negative semi-definiteness which cannot establish asymptotic stability directly. So at the end you have to invoke Lassalle's inference principle. Okay, please try. I will also. First of all, the case is how would you choose the Lyapunov function, right? Again, like when the moment that is you could relate with this kind of thing, especially if it is a kind of nonlinear spring mass damper system, then how would you form the V function? There will be potential energy plus kinetic energy, right? So in that case, you will write V as, of course, that is one. Had it been a linear spring mass damper system, we generally what do you take? That is. That is for simple pendulum. If it is spring mass damper, then of course that is 1 would be half mv square. In terms of state variable, it would be half m x2 square, right? And then for the spring, how would you write? In general, if it is non-linear, how do you write? That would be
A1 plus x
kx dx, right? And that is if the displacement is, or here you can write that, suppose if that is x1, k integration x1 dx1 and it is up to x or y, whatever may be the displacement. In that way. So similarly here also you have to focus, that is if it is a h1 into x of 1, similarly you will have to take that term. That is only the trick. Assuming that this is going to be the term that is which corresponds to either the nonlinear spring or even that is in this case also a similar term would be there. So that if you integrate that one, then it will give you the kind of potential energy. Okay. Of course, if it is an RLC circuit, we cannot say potential energy. Then it would be the energy. It will be for the one from the C, one from the L, right? Like half L square and half CV square. But the genetic formulation happens in that way only. So here exactly in the same way, that is if you write, that is suppose there is integration 0 to x h1 of x into d of x1 and plus half x2 square. Then let's see that is what happens. Okay, if that is the v function, then what will happen? If this is our Lyapunov function, then first you have to check whether really it can be considered as a Lyapunov candidate, right? So, first of all, that is, what are the properties? Let's see. Can I write that is V of 0 equals to 0? Regarding the first term, we don't have any doubt, but regarding the second term, if there is no displacement, then of course it will boil down to 0, right? So then that is, it would be like 0 only. Then the second one, that is whether V of x is positive definite or not. That too is satisfied for this, because that is for all non-zero x, the first term it will be always positive, and the second one also, that is because of that property, x into h1 of x greater than 0, so it will give you 0 only. Sorry, it will give you positive term only, right? So that's why there is addition of two positive terms, it will be positive always. So like v of x is positive definite, okay? Whereas if you have any doubt, like please consider this one, that is whenever you have a displacement, like whether it is a non-linear spring or a linear spring, it will always give you a positive thing, right? Because it's a kind of potential energy which cannot ever be negative. That is the clue, okay? And then v dot x that exists and continuous. Is it fine? Now you try to find out the v dot of x. What did you write for the second term?
h1 x1
Into x1 dot, right? That is the rule of differentiation according to Leibniz.
differential identification.
Exactly. So this case is the rule of differentiation by Leibniz. That is when you have an integration term, but it is a continuous function. If you wish to differentiate, then that is how would you differentiate? Simply this integration will go off, right? And then that is ultimately, this is even we don't know exactly about what is x1. So if this integration goes off, then simply it is going to be that is h1 of x1, and then x1 is a time variable. So then x1 dot, right? That is called like Leibniz rule of differentiation, and that guides us how to differentiate a function within integration. Okay. If you have forgotten Leibniz rule, you can check. So this one is going to be h1 of x1, x1 dot. If you have any doubt up to this one, please feel free to ask. And I suggest that is like, you might have forgotten the Leibniz rule of differentiation. You please check it, okay, after the class. then here is what is going to happen. Now, that is, if you substitute the expression for x1 dot and x2 dot, what this is going to be? And then x2 dot means this one. So, minus x2 h1 x1 minus x2 h2 x2, and what about the second one? Plus
H1 is 2.
exactly. So here we can see that is easily these two terms are cancelled, and then what is left? x2 h2 x2, right? According to the property, that this is going to be, it seems that it is negative definite, but it is not negative definite because of the same reason that it depends only upon one variable, right? So this is lesser than or equals to 0, negative semi-definite case. That's what I was talking about. Once again, when you have x2 into h2 of x2, you may, that it seem to be negative definite, this term seem to be positive definite. Why? Because here we have that criteria, yi into hi of yi greater than 0 for all I not equals to 0, right? But here, as a quadratic function, it is not negative definite, right? Because it depends upon only one of the state variable, not both. So that's why it is only negative semi-definite, and which implies the boundedness of the trajectories. That means just stable in the sense of Lyapunov, not asymptotic stability. But it, as you know, that is under the negative semi-definite case, the negative definite can also appear, but that is not readily understandable from this. So for that we have to either change the Lyapunov function, or else we have to apply Lasser's invariance principle, right? So, and like to be more specific, Barbashin's-Krasovsky, the theorem 2 which we learned last day, where you have to check that set, it cannot contain any non-trivial trajectory other than the trivial one, right? Which can stay identically within that set. So that is basically what we are now going to apply, right? So can you do that? Can you do that analysis? So that is, if we start once again, that is v dot of x identically equals to 0. Mithian guys, like please look at the board. Like let's see that is how we can do the Lasser's, as we can apply the Lasser's invariance principle. That is one more time, that is we are going to find out that largest invariant set in the sense where v dot of x can remain identically equals to 0. That means not only 0 for some time, that is once it has become 0, it will be 0 for all future time, right? That is the meaning of identically equals to. Then if we are trying to find out that set where v dot of x will be maintained 0, right? Is it clear up to this much for all of you? So v dot x identically equals to 0, that will imply, what will imply from this? x2 identically equals to 0.
So, but
Huh.
H2 0 is 0. How can we both 0? Because the AND condition is applied with the property that hi 0 equals 0.
Huh.
So, if H2 is also 0,
That means it is also like a kind of a positive definite condition, right? That is for all non-zero argument, this will give you positive, but it can be 0 only at 0.
what I am trying to say that if H2 identically is 0 from that condition, that means H2 of 0 is also identically 0, right? Because for the particular condition that hi of 0 equals 0 for all.
Okay.
That doesn't.
If I write it the full expression, then it will be clear. That is identically equals to 0 means full of this thing, h2 into h2 of x2 that is identically 0, right?
So either
Now,
of them is 0.
but can it happen? Because here, what is the first condition? That is this x2, or suppose this is y into h of y, that is positive definite, or that is positive for all non-zero y. And it can be 0 when y equals to 0. So together, what does it imply? Exactly, x2 identically 0.
This sounds absurd because 0 multiplied by 0 equals 0. Sometimes we avoid that part. Like both of
Right, here what is happening, so here what is the condition? That is h2 into h of x2. That is, if I write it separately, h2 into h of x2, that is greater than 0 for all x2 not equals to 0. That is the first condition, and that is h2 of 0 that is equals to 0. That means if x2 is 0, then it would be 0. Then automatically this whole thing will be 0. And when that whole thing 0 is possible? Only when x2 is 0. Are you getting now? So all of you please think about the condition, that is Orithra had a doubt, that is from this v dot identically equals to 0, that is how can I write x2 identically 0? Please tell me whether you are convinced or not. That is x2 into h2 of x2, that is identically 0, and it can happen only when x2 identically 0. Why? Because if x2 is not 0, then x2 into h2 of x2 would be positive. That is the reason. Okay? Arithro, is it clear now? In a simple sense, it is like this h2 of x2. This means as a d. If it is a like damper, simply suppose linear damper, then d into v, right? And then that is then if I write x2 into h2 of x2, then it is d into v square. Okay, so which is always positive for all v not equals to 0. Now, if somebody tells you that dv square that is equals to 0 or identically equals to, then what will it be? When v identically 0, right? That is what we are getting here. So this will imply x2 identically 0. Okay? Then it will also imply x2 dot identically equals to 0. There last day I said, maybe some of you had some doubt. 1 second, let me write. Last day at the end I said that is suppose x equals to 0 for the time being, okay, at a time or for some time, then I cannot guarantee that is x dot also will 0, right? At the same time, that is if you get x dot equals to 0, that too cannot guarantee that is x equals to 0, right? Because this one is about the minima or maxima condition, right? And then this one, like suppose just you are considering a sinusoidal or cosinusoidal wave, when it crosses the time axis, then at those points, like x is 0 but x dot not equals to 0. So please be careful about that. But here, what we are saying that is when if you say that is x identically equals to 0, by this particular notation, what do we mean? That is, this means that is xt equals to 0 for all t greater than equals to some particular time tf. That tf is the time where x is coming to 0, and counting from that second for all subsequent time it will remain 0. That is the meaning of identical equals to. Now if that is the situation, suppose a variable like it is 0 for 1 hour, that means now there cannot be any rate of change. That is the concept, okay? Only under that situation we are saying all this. But once again, please remember, if a variable is momentarily 0, you cannot claim that its derivative is also 0, okay? Now, is it fine up to this much? Now we have to apply these conditions back to the dynamics, right? Now x2 identical equals to 0. That means x1 dot identical equals to 0. So x2 identical equals to 0 will imply x1 dot identical equals to 0. And then, okay, first equation fine. Coming to the second equation. From this one, for the first equation. And now from the second equation, x2, if you put x2 dot identical equals to 0, okay, and then your h2 x2, that is also that is going to identical equals to 0 from that dynamic condition. Sorry, from Liapon of what we have got. Then what would you get? So, and from here what did you write? That is x2 dot identical equals to 0, and finally it will happen h2 x2 identical equals to 0. That is where we should have written if you include this step in between, then it will be further clear. Is it fine? That is, first of all, x2 identically 0. That implies from the first equation, x1 dot identically equals to 0, right? And then from the second equation, what do you get? If x2 dot identically 0 and h2 x2 identically equals to 0, it will imply h1 x1, sorry, h1 of x1 that is identically 0. Now you come to this condition, when this h function can be 0, only when the argument is 0. So if h1 x1 is identically 0, that will imply x1 identically 0, right? So finally, what is the conclusion? What that you have get? That is x1 identically equals to 0, x1 dot that is also identically equals to 0, then x2 identically equals to 0, x2 dot that is also identically equals to 0. Right? So this means actually your this trivial solution of the state equation xt identically equals to 0. Now once again you please go back to theorem 2 which we learned last day, and specifically try to match with the last sentence. Sutashu, what was the last sentence? Could you please read out? Last sentence of theorem 2.
So let omega naught belongs to D,
Huh.
where V dot x equal to 0 and omega naught cannot contain any territory
Huh.
that can remain identically in omega naught except the trivial solution xt equal to 0.
Huh. So here, when we are trying to find out that is the set where V dot is identically equals to 0, that means we are trying to find out that set omega naught, isn't it? So now we have shown that within omega naught, no non-trivial trajectory can be there, right? Except the trivial trajectory xt identically equals to 0. In that way, theorem 2, which is nothing but Barbashin-Krasovsky's principle, that is being applied here to conclude asymptotic stability. And if you see for that, the positive definiteness of the V function is required, that is which from the V function it is positive definite, but V dot is not negative definite, it is only negative semi-definite. That's why we need to take the help of Lassal's or Barbashin, whatever. And then finally we are reaching the asymptotic stability. Here you can ask that, sir, can we apply the theorem 1? Yes, you can also apply the theorem 1, but with theorem 1, what you can, like up to which you can reach, only you can say that is like xt will reach the largest positive invariant set M as d tends to infinity. There it is not guaranteed that the trajectory will reach the origin, okay? That is the reason why we apply the theorem 2, especially if we have to reach asymptotic stability, okay? And the two practical examples, one is the nonlinear string bus damper, nonlinear RLC example, that is example 3.14 from Shorter's book. Other one we already did, the nonlinear string bus damper system, okay? So now I believe that is you were like fine with Lassal's invariant principle. So that is, we will take one more example. Please check the whole process, because as this is like one of the vital tool of nonlinear stability analysis. Please check the whole thing and tell me if you have any doubt. Nitisha, last day you had some doubt. Is it now clear? The example that we did, that is also, that is from Khalil's book, okay, probably example 3.8. Immediately after Lassal's invariance principle, you will find that example in Khalil's book. And then the second part of this example is, can we establish global asymptotic stability from this? For that, what do you need to show? That is a Lyapunov function is a radially unbounded function, right? And the this definiteness of the semi-definiteness condition that extends for the whole R2, right? So that is probably 3.9, most probably from Khalil's book. here if the argument goes on increasing, that means displacement and velocity, or even in case of if it is a nonlinear RLC circuit, then the current and the voltage, then like can't I write that is V of x goes to infinity as norm x goes to infinity. That is, as the argument, I mean the state variables, if their magnitude keeps on increasing, then V will also increase, right? And ultimately, that is, if this function, that is, if you assume that is okay, this function can lead to infinity, that is, as its argument y goes to infinity, then this V function will become radially unbounded, right? If it is so, then after that we have to check that is whether this V dot, that the full analysis what we did, whether that can be extended for the whole R2, right? I mean the whole state space. So let's see. So V dot, what did we get? That was minus x2 h2 of x2, right? That is lesser than equals to 0. Here, that is, I can easily write for all x2 belonging to R, sorry, right? And since this is independent of x, so this is true for all x1, x2 belonging to R2. Fine?
Sir,
Yes.
sir, will it not depend on what the function h1 is? Because if after integrating we get like 1 by x1 or something like that, then as x1 and x2.
No, because for such cases, because originally if you see the properties of those two functions, that is how they are defined. That is yi into hi yi greater than 0 for all yi not equals to 0, and hi of 0 equals to of 0. So that's why the other type of functions, what you were thinking, they will not appear here. So this is only for a particular class of functions. One example is nonlinear RLC and then nonlinear spring mass damper. Have you understood what he is asking? He is saying that is while integrating, if we somehow get any kind of nonlinear terms, or that is which can change the sign of the function, then we cannot write it exactly. But here the function is like that, that is which should satisfy both these properties, right? So whenever you have that is y into h of y, that is always greater than 0, whatever may be the y, as long as it is non-zero. So that's why the possibilities what you are thinking, that maybe 1 by y or y cube, such type of terms, that is which can change the sign, that will not happen for this class of functions, okay?
So what about 1 by 1?
1 by y, that will not happen, because in that case the definiteness won't be maintained, right?
So also if you put 0, it would be infinity.
But here it cannot, like it is 0 and it is like at least that is here it is 0 means it can go to arbitrarily high, but within the finite zone of the argument it cannot go to infinity. That means there is no question of getting finite escape time kind of thing. That is guaranteed. So this is one thing, I believe everybody will agree with that. Then the subsequent analysis. Here also, we don't need to restrict x1 or x2 within a range, right? If you remember the example of simple pendulum, so there that is for the definiteness of the v function, or we need to restrict that x1 or the theta in between minus pi to plus pi. But you check this whole process which we just derived. For that, you don't need to restrict x1 or x2, right? So that's why this analysis we can readily extend for all x in R2, right? And at the same time here, if this function, if this is radially unbounded, then the whole V that is also radially unbounded, from which you can extend this result to globally asymptotically stable. Okay? So in that way, that is, we can apply the global asymptotic stability condition for nonlinear systems as well. Okay? So that is the second part of the example. This is also there in Khalil's book. So today, after the class, you can check. Now, I hope you have also understood that is why the same analysis doesn't apply to the example of simple pendulum. Why? Because when you are considering the V of x, then if you put theta equals to pi, then 1 minus cos pi, or even that is from at 0 or other thing, they will become 0. That is a difficulty, right? So that's why you cannot extend beyond plus 2 minus pi. U input. This is just an extension, you think about it. That is, at this moment we are not going to solve this, but why do you need it? Or that is, what kind of systems can be like cited as an example, or that is why these particular properties we are interested in learning, that I will tell you. Okay?
So why here is a single variable, right? Why are we looking for transposition?
That is in general. At this moment it is scalar, you were right, but it can be a vector as well. Input output and stability will come later, but at this moment it is input output. Why we are thinking about input output representation? Because as you know, that is in the nonlinear system, there is this asymptotic stability that is not the ultimate. Are you getting? That is maybe last semester I told you that in case of linear systems, that is if you can establish asymptotic stability, then that is everything is fine, because in case of LTI, what are the two main type of stability conditions or stability concept you learned? One is asymptotic, another one is BIBO, right? Asymptotic. I should not write or.
Only one is sufficient to
That is asymptotic, it implies BIBO. Okay. And then, or not only that, that is asymptotic stability will also imply total stability. What is total stability? That means asymptotic means you are checking about that is xt equals to e to the power 80x0, right? You are checking about the stability of whether the system that is will go to origin from x2, right? So whether x0 goes to 0 and t tends to infinity. That is asymptotic stability.
X of t tends to 0, right?
So starting from that is what I wanted to mean. In that sense, like, but you are correct. That is here I should have written that is xt tends to 0 as t tends to infinity, right? So what I am saying that in case of LTI systems, if you can prove that it is asymptotic stability, then at the same time it is totally stable. Totally stable means that is asymptotic stability in presence, the concept kind of asymptotic stability in presence of input. Here, that is what I wanted to show you, that is this part is only the free response, that is in the absence of input. Asymptotic stability says that is if like A is Hurwitz for LTI of course, then xt will go to 0 as t goes to 0, right? So this is asymptotic stability. Now what happens, that is if you have the term here like integration 0 to t and then e to the power a t minus tau d u tau d tau, who will guarantee that this will remain a bounded function? So for LTI with asymptotic stability is so powerful that it can guarantee that this will remain a bounded signal, that as long as u is a bounded signal. Okay, in that sense, that's why for LTI system asymptotic stability is the ultimate. Now the same thing we cannot say in case of nonlinear systems. For nonlinear it may happen, that is from the Lyapunov analysis we got asymptotic stability, okay, a system which is asymptotically stable. Now it is directly asymptotic stability cannot guarantee that is what will happen when there is a non-zero input. Okay, that is one of the problem with nonlinear system. So what is the takeaway point? In case of nonlinear systems, asymptotic stability in general does not guarantee total stability. Okay. So in case of nonlinear systems, asymptotic stability does not in general guarantee total stability. Now total stability means like the boundedness of the function in the presence of non-zero input.
Will you repeat again why it's not enough for non?
That is, In case of linear systems, it consists of free response and forced response. Then applying the asymptotic stability, that is from here also. See, A is Hurwitz, right? A is Hurwitz, B is a constant matrix of all finite terms, and then if U remains bounded, from that we can show that is this result of the integration, it will also remain bounded. Okay, so that by applying from the asymptotic stability condition, we can easily prove that. But that is not true for nonlinear systems in general. So what I said, that is asymptotic stability in general does not imply total stability. Total stability means this boundedness of the state of the stability of both the free response and the forced response. Okay, so this part is the free response, this part is the forced response. Now when you apply Lyapunov stability, then we conclude the xt will go to origin as t tends to infinity for nonlinear systems as well. So the asymptotic stability part is covered, okay, but that analysis cannot readily guarantee that the force part will also remain bounded in presence of even bounded input. That is one of the problem with the general systems, because we don't know what kind of nonlinearity is there.
In general, whenever we talk about nonlinear system, we just prove it even asymptotic stability exists, system is stable.
So that's why in case of nonlinear system, the stability concept is not only up to asymptotic stability. So for nonlinear systems, we highly need the total stability concept. Total stability means that is it consists of asymptotic stability and of course the boundedness of the state in presence of non-zero input. So total stability, it is actually asymptotic stability plus boundedness of the states in presence of ut not identical equals to 0. That is about total stability. Okay? Are you now getting? So then that is how to establish this total stability. For that is we need the input-output stability kind of thing. So there you have two type of concept. One is input to state stability. Input to state stability. Another one is input-output stability. In the robust control class, we were talking about LP stability, if you remember. L2 stability, L infinity stability, they are the input-output stability. That means, that is, if you can write the LP norm of the output signal is lesser than equals to a finite gain into the LP norm of the input signal. For a dynamical system, if you can represent, we discussed a little bit in the robust control, right?
Yes, sir.
Beer lemma, that is for linear. This one is for the non-linear. Because for the non-linear, you don't have the linear time frequency domain response of the transfer function is not available. So for a non-linear, linear or non-linear, this is the generic representation. That is, suppose this L2. Now, those who don't know about LP norm, it is simply like suppose L2 norm. Now, what do you mean by the L2 norm of a signal? That means its energy content. As simple as that. You don't have to complicate. L2 norm means the energy content of a signal. That means if somebody asks me, that is, sir, how do you represent the L2 norm? Can anybody tell me that is what will be the formula, how to find out the LP norm of a signal? 0 to infinity. Suppose you have the signal ft. Okay, if it is a scalar signal, then simply it would be ft square dt. Now an L2 signal means whole this integration, that result must be less than infinity. Okay, if it is so, then it is called, that is f. If somebody say that is f belong to L2, that implies it's and then whole root under, that is the L2 norm. So if somebody says that a signal belongs to the L2 space, then what does it mean? That means that is if you find out the energy, why this gives you the energy? That is any square of a variable that gives you the instantaneous power. If you integrate it over a certain time period, it gives you the energy content of that signal. Now this is for 0 to infinity, that is total energy content. And then since it is a norm, you are getting a square root, say for example in Euclidean norm or in all other norms you have the root under. So this gives you the L2 norm of the signal f. If it is less than infinity, that is if it is a finite value, we will say that this is a L2 signal. Similarly, it can be for L1, for L, other L. So in that sense, we call LP signals. Okay. At this moment, we can simply talk about the L2. So that is the situation. Now, that is if you have a nonlinear system, like suppose you have x dot equals to f of x, okay, plus g of x into u. Then that is if somebody asks you that is it Bibo stable, then we cannot apply the techniques which we learned for LTI, right? Then you need this kind of formulation, which is called input output stability. That is, what does it say? That is the L2 norm or suppose LP norm of the output signal. If that is lesser than equals to some gain, this gamma, this is called the finite gain. If a system satisfies this relation, that means this input output norm that will satisfy this relation with a finite gamma, then it is called an LP stable system or an input output stable system with respect to L2 norm. Okay. Now if this gamma is not finite, then it is not input output stable. Okay. That is the concept of input output stability. Now can anybody tell me that okay? Can anybody tell me what is input output stability? Sorry, input to state stability, this is only input output. Input to state stability.
So U will replace by X.
That means, that is suppose this is X,
Why
right?
will it replace by X?
No, U is not going to replace by X. What did I say? That is, if this is the X. Now, for bounded U, can we show that is this X will always have bounded value? That is called input to state stability. Once again, I am explaining with respect to LTI only. Suppose this is the whole state equation. In the present day, it has a free response as and forced response as well. Now, if somebody asks you that you show that xt will always remain a bounded signal as long as u is bounded. If that is the case, then it is called input to state stable. Now that is bounded, of course, then again the norm thing will come into the picture. That is norm of xt. That has to be like less than infinity. Now, what type of norm? Again, that mostly that is we can think about the L2 norm. If it is L2 norm, then we are talking about the energy content. If somebody says L infinity norm, then only about the magnitude. That is nothing but L infinity. L2 means the energy content, and then L1 means the whole integration, absolute summation, and L infinity means in terms of the peak value. So the Bibo stability that we say or that we know in case of LTI, in terms of L, that is simply called L infinity stability. Bibo stability, that is called L infinity stability. Now you can of course ask that, sir, why you were saying that it is L infinity? Because then I have to define the L infinity norm. If I say that is L infinity norm of f, which is how we can write?
Maximum of
not max. Here we have to start with sup. So it is supremum over all t belong to R. Then Kashinath, if this is the definition of L infinity norm, what does it mean? That is the maximum value or the absolute value of the maximum. That means whether it is a positive peak or negative peak. That means if you have a signal like this, suppose this point is your 500 and this is the highest of all the peak, then its L infinity norm is 500. That's why I said that is this bounded input, bounded output. Is that with respect to energy or is that with respect to the maximum value or the amplitude? Of course with respect to amplitude. Once again, Lebow stability in case of ATI system, is it with respect to the energy content or with respect to simply the maximum value of the signal? Maximum value. That is the reason why this Lebow stability is equivalent to L infinity stability. You can answer this, sir, why do we at all need this LP stability concept? Because as you step into nonlinear domain, you cannot say directly Lebow stability, or you don't have this ready-made expression. That is the main problem with us. As long as you have an LTI system, this XT, this bounded, like closed form bounded solution, everything is available to us, and subsequently all the tools, right, we can easily apply. But in nonlinear systems, as you know, that is the nonlinearities can be infinite type of nonlinearities. And when you talk about a generic nonlinear state equation, then also we cannot really guarantee the global solution of the state equation. That is another problem. So first problem is whether XT exists, that is when existence and unique problem. And then even if it exists, then finding a closed form solution of a nonlinear differential equation, not an easy matter. So that's why that is directly analyzing the boundedness of the whole XT, that is really very difficult. So all the formulas that which we have for LTI systems, they mostly do not apply directly to nonlinear system. That's why we need some other type of techniques. That is the reason why we shift to LP stability in case of nonlinear. Okay? So you have understood L2. This is nothing but your L2 norm. You have understood L infinity norm. Then if I ask you what is L1 norm, because when we are discussing at least that is L1 also you should know. If I write that is LF belongs to L1, then what does it mean? That is this L1 norm is finite. And how do you write L1 norm? That is integration 0 to infinity absolute value of that signal dt less than infinity. That is your L1 norm, right? In general, you can easily find any book or in the internet the expression for LP norms. Okay, so this is what like absolute, like you are completely like summing up the area of the signal mod of ft, right? Please note that like all these, like whatever formula I have written at this moment, they are for scalar signals. Say so, okay? But if it is now a vector signal, then what would you do? Simply this one is going to be replaced by ft transpose ft. That means the vector case we can readily handle, okay? For continuous, since that is you are beginner, so that's why to make it simpler, I have written for CISO, but it can readily, we can write it for multivariable signals as well. That is the meaning of input-output stability, and also we have discussed the requirement, that is why the LP stability concept is required, okay? Now, that is, I also discussed in short about input to state stability. Input to state stability means if somebody tells you that is U N2 that is finite, that is U is a N2 signal, okay? So this is less than infinity. Does it guarantee? This is the input to state stability problem. similar to Bibot stability. See, when we discuss Bibot stability, what do you say? That is for all bounded input, whether your output is also bounded or not, right? In that way, we say Bibot stability. Now, input to state stability means if somebody asks you, your input is bounded. Now, bounded in which sense that we don't know. That bounded it can be with respect to L1, with respect to L2, with respect to L infinity. Right now, that is I am simply saying that is if somebody like asks you, that is, hey, you are applying the input to your system and your input is bounded, whether your xt will also be bounded. If that is the question, then it is called input to state stability. So that's what I wanted to represent. That is, suppose here I expressed with respect to L2. It could have been with respect to L infinity or L1 also. So here what is mathematically what is the question? If U belongs to L2, the question is whether X belongs to L2.
So we
That-
can generalize with LP also.
Huh. So that is the question of input to state stability. Okay, and ultimately in layman's term, it is the question is about whether your xt will remain bounded for all time if your u is bounded, and then we will talk about input to state stability with respect to L infinity now. Are you getting? If I say that is like for all bounded input, whether your xt will remain bounded for a nonlinear system. So it is like we are going to extend the Bibot stability concept to the nonlinear systems, but not only to output for the state. Are you getting? Bibot stability in case of LTI, we talk about the whether the output remain bounded. But here it is not only about the output. If it is only input output, then readily we have the LP stability. It is the case of that you have the state. Like then the question is if U is bounded, whether X will remain bounded for all time or not. Okay. So that is the concept of input to state stability. It is also there in Khalil's book. Maybe we don't have that much time, but I wanted to give you the glimpse of all the concepts so that later if it is required, you can directly read it from Khalil. Now if you, that is something more, that is if you ask me, okay sir, we have understood the problem, now if we have to mathematically establish that, what kind of tools we need, right? That will be a valid question. Even if we like don't learn this at this moment, but you should always know that is in which way it will direct. Are you getting my question? That is if somebody asks me, that is okay, you know the concept of input to state stability, input output stability. How will you evaluate? We have already learned how do you evaluate input output stability, right, for nonlinear systems. Now if somebody asks you, that is how would you evaluate input to state stability for a nonlinear system, what kind of tools you will need, what did you say?
So there cannot replace y with x.
Directly, that is there, it can be, but that won't be such a elegant fashion. That is the problem. Because here that is due to this integration and all the terms, because here output you have a direct term that is y equals to h of x or g of x. So in that way, here also that is you will have challenges, but directly we cannot write that in that fashion. Okay? Because what is the difference between that? That is that once I tell you the logic, like the technique for input to state stability, then it will be immediately clear. Please note that for input to state stability as well, we apply the Lyapunov, and that is the Lyapunov stability analysis for non-autonomous system. So far what we have learned, that is in presence of U identically equals to 0. But Lyapunov stability is not only for autonomous system, it can be for non-autonomous systems as well. Non-autonomous means you can include some perturbation, you can include time dependency and also input terms. Okay, so in the presence of input, there also we can apply the Lyapunov, but that is not as that straightforward we have learned. Okay, why? Because when the U is there, that means continuously an exogenous signal is there within the system, its effect is continuously coming. Then these V functions, I mean the energy light functions, how would you say the positive definiteness or negative definiteness? Like simply, that is I pose a question. Here we are saying that is V of x, that is positive definite, and then v of x equals to 0 equals to 0. Now if it is non-autonomous system, then here you will find the v of x comma t comma u. Now that causes the main trouble. Earlier v was a function of x only, but whenever it is a non-autonomous system, then v may also depend upon time if it is a time varying system, and also on the input, right? And if it is so, then the establishing this positive definiteness or negative definiteness, that is really difficult. So for that, if you see chapter 4 of slotting, then you will find that is for that we need the condition of uniform stability. Maybe you might have heard that term. Like so far we understood asymptotic stability, global asymptotic stability. One more term we'll have to learn, that is called uniform asymptotic stability. Uniform asymptotic stability. You can ask like, sir, why is keyword uniform is coming? That means if the stability conclusion is there for any initial time, that is called uniform asymptotic stability. And for that is this positive definiteness and negative definiteness, you have to use some other kind of tools which are called class A function. Okay, don't worry at this moment. If we get time, we will learn. But if somebody needs, you can readily just scroll through the pages of chapter 4 from slotting. So that is the difficulty, or the something difficulty in the sense that is you have to know more mathematical tools if you have to analyze this. And now, Sutosho, coming to your question, what did I say? That is input to state stability, that requires your Lyapunov. Lyapunov for non-autonomous system. Okay. Now, if it is input-output, then there we directly use all the L operators, not Lyapunov. That's why we cannot directly get that expression. That is the main difference in the difference in the tools which we'll apply. Once again, for input-output, we mainly, that is based on operator approach. Whereas input to state stability, we still use the state equation and P function. If you wish to say like something more, it is there in Khalil's book, and the authentic book is Vidyashagar's nonlinear analysis. There is another nonlinear system book by Professor A. Vidyasagar. Probably the title is nonlinear. What will be titled here? Nonlinear systems or nonlinear analysis. So in Vidyasagar's book, all these things are there. That is how do you frame or establish LP stability of the system. Okay. Last year in robust control I taught that, but later the students was not happy because it was too mathematical. So that's why this time that actually the part is wholly from functional analysis. So this time I am not teaching that topic. And because of that reason only, maybe some of your seniors told you not to take robust control. That is the reason. Although this is a very highly important topic, but at the same time it is very mathematical, because L stability it requires all these L operators and the other thing. So that requires like quite ample knowledge from functional analysis. That's why it is really mathematical. Although I tried my best, but they didn't like, and that's why they suggested not to take robust control. Anyways, this is about, and then today I didn't get time to finish. Please, I already told you that is the example 3.13 from Slottin's book. That is the Lyapunov applied to a system having limit cycle. That is highly important. Okay. Example 3.13, page 71. So that is your just one small home task, because this problem is, although it is solved, but it is only partially solved. You have to understand what they wanted to express. Okay, and this is something that is here, like auditor. Do you have any idea at this moment? If this is the representation, then suppose y means it is x2 and u means whole of this. Does this kind of system give you this kind of factorization? মইনা তুমি হাসছো মানে হচ্ছে টাইম এক্সিড হয়ে গেছে। তুমি লাস্টের দিন বলেছিলে না যে when you laugh that means that is your the limit has been exceeded. So anyway, then we should stop. Okay, this is really an interesting problem. I give you a small hint that is this will lead to passivity for nonlinear systems. You already know the linear cases, positive real, right? Last semester I told you that is we will learn for the nonlinear. So this will go to the nonlinear, and of course we are this passivity. You can ask, sir, why you are bringing passivity? Because this kind of thing even can give you a very good result for interconnected system. So far, whatever you have learned for just for stability of one single system. Now, that is when it comes to when the controller will come. Of course, you will have to handle an interconnection, a plant and a controller, right? So then you have to learn the technique how to handle or how to analyze the stability of an interconnected system, which for general nonlinear system is not at all straightforward. So for that is we have like 3 or 4 good results. If the system satisfies this kind of property, then establishing the closed loop stability is not that tough. And of course, for some small classes of system, we have some good results, but not for all. So that's why always analyzing the stability of nonlinear systems is tough, and if it is interconnected nonlinear system, then it is tougher. Okay. So in that way, that is we will try to learn 3 kind of things. One is nonlinear L2 gain concept, like nonlinear L2 gain stability for interconnected, passivity, and then negative imaginary. 3. হ্যাঁ ঠিক আছে, অরিত্র অত চাপ নেওয়ার কিছু নেই, আমি চেষ্টা করবো যে ইজি করে পড়ানোর জন্য। হ্যাঁ না ওটা লাস্টের দিকে পড়িয়েছিলাম, এবার দেখা যাক দেখি কতটা করা যায়। ওকে